All right, so what do you remember about first principles of derivatives? The definition of a derivative. Can you write the formula for that? I'm curious. This has been a long time. We're almost halfway through the course, and this is something that you're going to have to do on the exam again. So a little bit of exam review today, I guess. But let's say f at x is some. We're doing derivatives of exponential functions today. So b to the x, where b is greater than 0, some value greater than 0, because if b was less than 0, if b was negative, it would be, think it's good. If b was less than 0, well, that's not a function. Like, it's not a function. It's not a continuous function that we can think about. If b is 1, it's also not very interesting because it would just be a constant, right? But anyway, let's say it's just a regular old 2 to the x, 3 to the x, 4 to the x, something like that. Does anybody even know what I'm asking? What is the definition of a derivative? Zach, you had an idea? What was the question you asked? Are we back to limit stuff? Why is he asking about limits? That's how the derivative started, the definition of a derivative. Very good. What is it? Oh my gosh, we're in trouble. Limit. So f prime of x equals, limit is, I'll get you started, h. Okay. Yeah, over x plus h minus x, which is just over h. Very good. Now this is coming back to us a little bit, remembering this. And do you remember, then we used this idea, for the most part, to derive all the rules that we've been using to take derivatives of polynomial-like things. Rational functions, polynomial functions, other things with like rational exponents, that kind of stuff. Right? Product rule, quotient rule, all that stuff, a lot of that stuff at least, we used the definition of a derivative to determine their the rules by which you can take the derivatives of things. But we didn't do that for trigonometry. Why? Because we don't have the math required to derive the derivatives of trig functions from first principles like this. It requires other math that we haven't learned. So we did it by inspection. Remember, we just looked at the graphs of those things and we kind of saw like, oh yeah, sure looks like cos, sure looks like negative sign. But we can go back for exponential functions. We can go back and use this for the most part. There's one part we can't do, and I mean, it's actually kind of an important part, but we can at least get part of the way there. So try to follow along. We can sub our function b to the x into this, because that's something you want to be able to do. So see if you can do that. What is it? Anybody know? Remember?
So to find the value for x, do we just use logs?
We were way ahead of us. I got to write the next step first.
Oh, okay. So, but we have to know. Okay, so x is the exponent. So x equals base b of log of f at x plus h inside brackets.
But you've done a step. If this is just, don't do any work, just sub in. If it's b to, if my function is b to the x,
Minus b of x.
huh?
Instead of f at x, we just put b of x.
But we're subbing into this. So yes, that's, now you're on the right track. Daniel, did you get something? B to the x plus h minus b to the x over h. So logs maybe, but let's not do that. Is there anything else we could do with this Does anybody have any ideas how we can start to, like, I don't know, manipulate, resolve, simplify it all?
I don't remember if that's going to simplify just to b to the h or b to the x plus h over x.
Okay.
I think it's just going to result in b to the h though.
The whole thing?
Like the top, I mean.
The top? Okay, but how are we going to do that? Zach, what do you think? It'd be nice if we could factor, but we can't factor. Not like this, at least. There's nothing I can factor out of this. What else could I do? Like, what can you do?
Like, since they're the same base, you can combine them somehow, but I don't remember how.
You're on the right track. This is a sum of things of the same base, so we can't really do anything with that, but... No? Anybody else? Can I do anything with b to the x on its own? Okay, I can take the log of it, but taking the log of something, like, I mean, I can't take the log of one thing in a sum. You know what I mean? So, I mean, I could, but that's not what we want to do. Is there anything I could do with h on its own? I don't think so. Is there anything I could do with b to the x plus h? Okay, so that's something at least. I don't know if that's going to help. Hold on. And this is because, I'm just doing this off to the side. Remember, if I have like x squared times x cubed, that's x to the 2 plus 3. So we went back the other direction. Not something we do very often, but useful in these kinds of situations for rewriting things, doing proofs, or that sort of thing. So all of this over h. Now what can I do? Now I can factor. I'm factoring it on top, but because it's a product, I can actually take it all the way out front, right? Nope, -1. Anybody know what I can do with this? This is something we've done before. You know?
I don't know if you can turn 1 into b to 0.
I can turn 1 into b to the 0. Oh, I could. I don't know if that's going to help. Something that we did before. Go ahead. Yeah, kind of. If it was a sum, it would be the limit of this plus the limit of this. So this is a little bit strange. In the next two steps, we're going to kind of flip-flop, but this limit is in terms of h. This has no h in it. This is a constant relative to h, not a constant in the function, but relative to h, this isn't changing. So this doesn't have to do with the limit. So by properties of limits, property number 3, we've seen this before. If I have constant times a function, I can bring the constant out. This is a limit in terms of x, so the variables are a little bit messed up, but I think you can believe me on this one. So I can bring the b to the x out, not just separate the limits. I can bring this straight out of the limit. Now, the problem is this limit is still indeterminate. b to the 0 is 1. 1 minus 1 is 0 over 0. This is still 0 over 0. We, unfortunately, don't have the skills required to solve this limit. Here's where I'm flip-flopping. This limit is a constant in terms of x. This limit has a value. We just don't have the skills to solve it. But in terms of what we're trying to accomplish, the derivative of the function, this is just a constant. It has a value. Okay? So it turns out, oops, I was going to make this another color. Off to the side here, turns out that the limit as h approaches 0 of b to the h minus 1 over h is equal to the ln of b. Pretty simple. So like I said, the math required to solve that isn't something we can just learn in a day. It's like a whole course load of work kind of thing. But The result is fairly simple. So we just actually found, we're going to talk about this a little bit later, but we just found out what the derivative of an exponential function is. If I took this constant and subbed it in here, so if it was 2 to the x, it'd be 2 to the x times ln of 2. Like that would be the derivative of 2 to the x. Okay? Yeah.
That's what's so magical about E.
This is what's so magical about E. What if the ln b equaled 1? Because it's kind of nice if it's a constant, but it's a constant of 1, then we don't have to even worry about it. So when is the ln of b? Remember, b was the base of the original function. So I just gave you an example with the base of 2. 2 to the x times ln of 2 would be the derivative. But what if it was a different base? When is the ln of b equal to 1?
So it's going to be 1. So E.
So how do I do this, though? Rewrite in exponential form. Base stays the same. B equals E, because the ln is log base E, so the base was E, to the 1. Rewrite in exponential form. So in other words, B equals E. So what is this telling us? It is something unbelievable just happened. Did you see it or did you miss it? It was like, whoa, what just happened here? No? You think I'm crazy? Okay, let me try this. Okay, so that's sort of the end of that. Actually, I'm going to write this out. So this would be equal to b to the x. We're going to come back to this later, times the ln of b. Okay, so that part is done. So if f at x equals e to the x, then f prime at x equals, this constant is 1 in this case. My base is now e. Ln of e is 1. So what is the derivative? Daniel?
Also E to the X.
It's just e to the x. E to the x times 1 is e to the x. That can't be true. Do you understand what this means? Remember when I said, like last week or something, you thought trigonometry was easy because the derivative of sine is cos? This is even easier. Derivative of this function is itself. Doesn't even change. Couldn't get any easier. Of course, when you add the chain rule and product rule and stuff like that, it's not like our math is done and now we're just going to sit around 5 days rewriting a function. But so there's a little bit more work to do. But the derivative itself is so simple. Couple other things about this, like what does it even mean for a function to be the derivative of itself? Taking the second derivative will be easy. Taking the third derivative will be easy. Like, right? It's not going to get any more complicated. But it also means, okay, that was a pretty bad graph, but here is y equals e to the x. So there's a graph of y equals e to the x, or sketch. If I pick some point on this graph, and I say its y value is 3, what do we also know? The slope of the tangent at that point is 3. Point on that curve. Interesting. And it also means the graph of the derivative will be like the exact same function, right? But again, this isn't true if you start adding things on to the function, but it's true for the base form. So you can see why This is one of the reasons why E is so important. Okay, in calculus, it has this useful property that its derivative is more simple than other things. And there are times where you get to choose the base you're working in. So if you get to choose the base and you're doing calculus, why not choose E? Because it's the easiest derivative. Otherwise, you have this nagging constant you always have to worry about. So E is really useful in calculus when you're doing exponential stuff because of this reason. But I'm going to tell you a little story, some background. You don't need to know this. We don't usually ask for this proof. We haven't talked about it necessarily, but we don't usually ask for it. So you don't need to necessarily know that proof. But I'm going to tell you another story about the discovery of E. So like a lot of things, E was discovered over time where they sort of estimated it to a couple of decimal places, then 3, then 4, then 5, then 100, then whatever. Then they realized that it's one of these transcendental numbers that like pi that never repeats and never ends. And then they discovered that it has all these other incredible properties as well involved in calculus and that kind of stuff. But I think one of the first ways that it was sort of approximated has to do with banks and money. It's kind of interesting. And like I said this the other day, like pi, E sort of pops up in all kinds of different places. Now, money is an exponential function when you're talking about compound interest, so maybe it's not surprising that it would pop up here. But go with me. If you don't know anything about compound interest, again, don't worry too much about this, just a story, but I think it's interesting. If you take some money, so let's say you take $500 and you put it in a bank account, if that bank account could pay you 100% interest over the course of a year, which no bank account will, but if it would give you 100% interest over the course of a year, at the end of the year, your money would double. You'd have $1,000. Easy enough, right? But there's this thing in interest where they compound your interest rate at different intervals. So your interest rate over the course of a year would be 100, but if it's compounded monthly, what that means is they take the 100% interest rate, divide it by 12, and give you those amounts of interest at monthly intervals over a year. But it's good because you'll actually have more than double your money, because when they add on the interest after the first month, the second month gets interest on that interest as well. So that's what I mean by it compounds. And then the next month, it's on the original amount and all the interest you've earned. So it's still 100% interest rate over a year, but it's compounded monthly. So if it's compounded yearly, if it's just for the year, your money would double. If it's compounded monthly, it more than doubles, 2 point something. If it's compounded weekly, it's even more than that, 2 point something higher. Daily, even more than that, 2 point something even more. And if you compound it by hour, by minute, by second, which nobody does, but like if you increased that compounding period infinitesimally small, so it's compounding constantly, that value approaches E by the end of the year. If you could get an interest rate that was 100% over a year, compounded constantly, infinitesimally small, then you would have the original amount times E by the end of a year. And so they knew this a long time ago, that there was this value that was being approached by this compounding period. They knew this. And then all of a sudden in calculus and all this stuff, this incredible number E comes up. All right, let's just write this out and then do some work with it. D of e to the x by dx equals e to the x. There's another way we write this. I'm going to do it just so you get familiar with it, because sometimes you see this in like programs like Desmos, that kind of stuff. D by dx of e to the u. Again, just a reminder of notation. This is saying we're taking the derivative with respect to x. But then my function is e to the u, not e to the x. U is some other function, probably in terms of x. Maybe it's x squared plus 5, I don't know. But it's some other function. So by chain rule, what will my derivative be? This is something we can apply and we can know. Exactly. So this is true of all functions. The chain rule is true of all functions. All right. So the y prime is e to the u times u prime. So e to the u is e to the 3x. Our u, in this case, is 3x. You can think about it like that, right? And then times u prime, what's the derivative of 3x? It's just 3. And we would probably write that as 3e to the 3x. So, I mean, it's important to notice the derivative of e to the x is e to the x, but the derivative of e to the 3x isn't e to the 3x. It's 3e to the 3x. Close. When you're taking the derivative of a constant times something, then it's just that constant times the derivative of the something. Like this is a rule that we know, so it obviously applies in this case as well. So this is going to be negative 7e to the 5x squared times the derivative of 5x squared. What's the derivative of 5x squared? 10x. And we would probably write this as negative 70x e to the 5x squared. Everybody okay so far? It's pretty simple, right? Now, we also want to note that we're not just taking derivatives of things, we're doing things with those derivatives, like setting them equal to 0 and determining where they do not exist and solving for where they equal to 0 so we can find points of inflection or critical values. Like that's what we remember that we do with this stuff. So if